Okay, so today we're going to be starting our thermochemistry topic, which is still part of Unit 3, Area of Study 1 of VCE Chem. And specifically today we're going to be discussing the combustion of fuels as exothermic reactions with reference to the use of the joule as the SI unit of energy, energy transformations and their efficiencies, and measurements of enthalpy changes, including symbols and common units. So within this DOM point, we're also going to be discussing enthalpy, what it is and how we use it. We're going to be discussing the law of conservation of energy and the implications of this law when it comes to thermochemistry. We're also going to be discussing endo and exothermic reactions, what they are, how they are different and how they are similar, and also how we identify them. We're also going to be discussing energy profiles, how we make them, how we interpret them, and how we read them ultimately. And the final section we will be discussing today is energy transformations and their efficiencies. Okay, so we're going to begin our discussion of thermochemistry with some of the key fundamental concepts that are really important to understand before we delve any deeper, which is enthalpy and conservation of energy. So for the purposes of VCE Chem, enthalpy, also known by its symbol H, is roughly equivalent just to energy in general, right? In more technical and advanced forms of chemistry and physics, there is a notable difference, but for the purposes of what I'm going to discuss today, just think of enthalpy as equivalent or analogous to energy. And we often measure it in the joule. And I've mentioned this before when I've been discussing different fuel energy contents. So whenever you think of joule or kilojoule or megajoule, etc., just think about it's describing how much energy something is producing or releasing, etc. Another fundamental concept we need to understand is the conservation of energy. Now, the word conservation kind of hints at what we're discussing here, but essentially what this states, and it's a very fundamental rule of thermodynamics, is that energy, which is basically what thermodynamics is all about, cannot be created or destroyed. So what that means is if we have any sort of difference in energy, that's because it's been converted from a different form. So when we talk further on about different types of reactions that release energy, that energy has been released. It's a bit of a misnomer, but it's been sort of, rather than being released, it's been changed into a different form than it was previously. So oftentimes when we talk about chemistry, a lot of reactions release heat, and this heat energy has been converted from chemical energy, which was stored in the bonds of whatever compound has been combusted, for example. And in a similar way, if energy is absorbed, that energy isn't just kind of going away somewhere and we can't see it. That energy is usually being stored or converted into a form that may be observed differently or is unobservable to us. So again, another example is heat energy. If heat energy is sort of absorbed, it's usually absorbed as chemical energy, which may not be as easily observed. So those are the fundamental concepts. Okay, so now that we've introduced enthalpy and the conservation of energy, we can now begin to discuss endothermic and exothermic reactions. So the first question that we're probably going to discuss is, well, what are endothermic and exothermic reactions? Well, the names themselves give us a hint on what they entail. So an keyword exothermic reaction is a reaction which releases, exo meaning outside, therm, heat. So it's a reaction that releases heat. And a lot of reactions are actually exothermic. So if we think about combustion, combustion is a very common exothermic reaction, but there's many exothermic reactions out, and we're going to begin to discuss them a little bit today. We also have endo, and endo meaning inside, therm. It's a reaction that absorbs heat. And these are reactions that are a little bit less common. But if you think about things like instant cold packs and things like that, they often rely on endothermic principles. So when we relate this to enthalpy, exothermic reactions have a change in enthalpy that's negative, and endothermic reactions have a change in enthalpy that is positive. So essentially what that means is this heat energy that is being released is coming from somewhere, and 99% of the time it is coming from chemical bonds that are being broken, and that chemical energy is being converted into heat energy. So I'll just write that here, chem to heat. And on the flip side, when we talk about endothermic reactions, the absorption of that heat from the surroundings is being absorbed to provide that energy to be stored in a different form. And usually that will be chemical energy. So this will be the sort of reverse. So heat energy is going into chemical energy, or being converted into chemical energy. Now, an important note is that there is no change in the amount of energy. So the system still has the same amount of energy it did at the start, because if we refer back to the conservation of energy, energy cannot be created or destroyed. So that's important to know. But the final thing with this is how they relate to energy profiles, which is what we're going to discuss next. Energy profiles are really important when it comes to thermochem, and they really help us visualize the exo and endothermic reactions we've been discussing earlier. So I think the best way to sort of go about this is just to draw them, and I'll tell you the sort of main features and the sort of differences between in endo and in exothermic energy profile. So we're going to start off with the more common energy profile that you're going to encounter, which is the exothermic one. And all energy profiles are just sort of graphs. So they look like this, with enthalpy on the y-axis and time or reaction progress on the x-axis. And all that means is that as we get closer, as we progress along this this x-axis, the closer we get towards this right side, the closer the reaction is to complete. So an exothermic reaction kind of looks like this. You'll have a section that's straight here with a little bump going down and going to a plateau here. So this section up here, this flat line, is the enthalpy value of our reactants. And this is basically just how much chemical energy is stored within the bonds of the compounds that are reacting. This little hump from the reactants, from the enthalpy of the reactants to this apex, is the activation energy. And this little plateau here is finally the enthalpy of the products that we've just formed. And the change, the difference between these two values is called the change, or delta H, the change in enthalpy. So the way we calculate this delta H value is by using the product enthalpy and subtracting the reactant enthalpy. So if we just give some random values, say this is about 70, give this 100, we'll say this is 30, the change in enthalpy will be 30 minus 70, which is negative 40 kilojoules. And we'll say this is in kilojoules, just for the sake of argument. And if you remember earlier, I did mention that an exothermic reaction has a negative delta H value. And that just basically means that the energy that once was stored in the chemical bonds of the reactants, some of that energy, in fact 40 kilojoules of that energy, has been released as heat energy. And it may also be released in other forms such as light or sound, but the majority is going to be released as heat. And the 30 kilojoules, that sort of makes up the total 70, has been maintained as chemical energy in the products that we formed. So the activation energy now is another important feature. And essentially what that is it's from the apex minus the H, the enthalpy value of the reactants. And essentially in this equation, it would be 100 minus 70, which is equal to 30 kilojoules. So yeah, that is sort of an exothermic energy profile. Now if we come over to this side, we're going to discuss what an endothermic energy profile will look like. And there are some key similarities. So again, same sort of graph looking structure, with the y-axis being enthalpy, and the x-axis being time or reaction progress, as I said before. And in fact, the reaction I will use is basically the reverse reaction of this. So if we start at 30 here, this can be our reactance going up all the way up to 100 and eventually plateauing here at 70. And again, this is also in kilojoules. So again, just going through the main features. So the activation energy here is going to be significantly larger. And remember, it is from the apex to the enthalpy of the reactants. So the activation energy here is going to equal 100 minus 30, which is equal to 70 kilojoules. And again, the enthalpy of the products is going to be 70 minus 30. So we'll write that here, 70 minus 30, which is equal to 40 kilojoules. And I will draw your attention to a few key points of comparison here. As we can see, as I mentioned before as well, the delta H value of endothermic reactions is always going to be positive, and we can see that maintained here. But we've also noticed that if we have two reactions that are basically the same, so this reaction could be considered the forward reaction, and this is the reverse reaction of this, the enthalpy change, the magnitude of the enthalpy change is the same, but the only difference is the sign. And essentially what that means is that the reaction itself, it kind of proves the conservation of energy concept we were talking about before. The same amount of energy is sort of lost or gained, so to speak, in terms of chemical energy. It's just whether that energy is going from chemical energy to heat energy or from heat energy to chemical energy, and that's reflected in the change of sign. Another point that's really important to understand is the fact that there's a significant difference between these activation energies. And essentially, what that reflects in reality is that these exothermic reactions are a lot easier to start. So at this activation energy point, this is when the bonds between the reactants are completely broken and allows us to make new bonds for the products. So if you require, in this case, more than double the amount of energy to get to that point, this reaction is going to take a lot longer and be a lot less spontaneous, whereas this reaction is going to happen a lot faster and a lot easier. So when we talk about exothermic reactions, oftentimes they're a lot more spontaneous and a lot more volatile in a practical sense than endothermic reactions, which are a lot more easy to control because they require a larger sort of initial input of energy. Okay, so the final thing we're going to discuss very briefly is energy transformations. And in essence, this is kind of everything we've been discussing so far with thermochem. But we're going to be going a little bit more in depth and specifically talking about the important bits about energy transformations when it comes to the study design dot point, which is really its efficiency. So the way I'm going to talk about this is frame it with some stuff that we've already learned through things like fuels. So electricity production from, for example, a coal-fired power station requires a few different steps and a few different energy transformations. So, in a simplified form, the chemical energy of the coal, the chemical energy of the coal is converted into thermal energy by burning it, and this thermal energy is then used to heat up some water, so that increases the thermal energy. So it heats up the air, which then heats up the water or boils it, and then that eventually, through various processes, goes through to turn a rotor, which is mechanical. And then this eventually goes to electricity or electrical energy. And at all these points, there is loss. And the more energy transformations we have, the more loss we are going to get. So in total, this process maybe have an efficiency of like 30%, for example. But other processes which have less energy transformations are going to be more efficient because there's less opportunities and less moving parts for it to sort of cause loss. Another example that we're going to encounter later on when we discuss sort of combustion of fuels is, warming a beaker of water. So if this is like a fuel burner, the energy that's released from that is going to burn this beaker, and then heat up this beaker of water. But the energy transformation that we are going to get from that is not going to be 100% 100% efficient. It may be something like 60% or 70%. Like it doesn't. It depends really on the apparatus we have. And so when we are doing things in a practical sense for chemistry, it's important to factor in the fact that, we talk about these different transformations from, in exothermic and endothermic reactions from chemical to heat or vice versa. But in reality, these reactions are not 100% efficient. And when we come more to the equation side of things, oftentimes this error is big enough for us to factor it in, and it can give us some wayward results if we don't. So that's just an important thing to consider. And it'll come up again and again when we talk about other things in chemistry as well.